Welcome to the deep dive. We are jumping straight into one of the most structurally surprising AI papers of the year. Seriously, this one fundamentally overturns a core assumption many of us have had about transformers. This is your technical shortcut to the insight. The paper is called Language Models Are Injective and Hence Invertible by Nicolau and colleagues. Okay, here's the rapid summary. The main takeaway. Standard decoder-only LLMs, think your GPTs, llamas, they're mathematically proven to be almost surely injective. What that means in plain English is the map from your prompt, the discrete input sequence, to the last token's continuous representation. It's essentially lossless. Yeah, those nonlinear bits we all assumed made it lossy. Turns out, not so much. And this injectivity is not just a fluke at the start. It gets established right at initialization, and crucially, the paper proves it's preserved through standard gradient descent training. To make this practical, they built SIPIT, sequential inverse prompt, via iterative updates. It's the first algorithm that guarantees exact recovery of your input text from the hidden states. And it's fast.
We're talking worst-case linear time, like T times V. The big picture significance. Hidden states aren't just fuzzy summaries. They are, effectively, the input prompt in disguise, recoverable. This is huge for transparency, interpretability, and even regulation. Okay, let's unpack that structural guarantee. Because honestly, for years, the standard view, the gut feeling, was the transformers had to be lossy.
Oh, absolutely. That intuition made total sense, right? I mean, you look at the pieces, layer norm smooshes things together.
Right.
Activations like GELU are non-linear, definitely not one-to-one functions on their own.
Yeah, many inputs can give the same output for GELU.
Exactly. And attention is doing this weighted averaging. So you pile up layer after layer of these operations. Why wouldn't you lose information? It seemed obvious the original input sequence details would just get washed out.
It did. But this paper shifts the perspective, doesn't it? It says, don't look at the individual components in isolation. Look at the whole system, the end-to-end function defined by the model's weights, theta.
Precisely. They bring in the heavy math. The key is realizing that all those building blocks, the embeddings, layer norm, the attention mechanism, the MLPs, even the residual connections mathematically, they're all real analytic functions of the parameters.
Real analytic, meaning super smooth, infinitely differentiable.
That's the idea, infinitely smooth. And this property is what changes everything. It doesn't mean the function can't bend or distort the space.
But it can't completely crush dimensions.
It prevents that kind of catastrophic collapse. There's a key theorem they lean on from real analysis. It basically says the set of parameters, the specific weight values, theta, that would cause a collision.
A collision meaning two different prompts, ands and prime, mapping to the exact same final hidden state.
Yes, exactly that. The set of weights where that could happen. It has Lebesgue measure 0.
Okay, measure 0. Let's make that concrete. If we imagine the huge space of all possible model weights, like a giant room, the bad weights, the ones that cause collisions, aren't like a whole section of the room.
No, not at all. It's more like a sheet of paper hanging in the room, or maybe just a thin thread. It's a lower dimensional subspace.
So when you initialize your model, you're essentially throwing a dart into that room, picking random weights using something like a Gaussian distribution.
Which fills the whole room, yes.
The chance of hitting that exact sheet of paper, that measure 0 set, is 0.
Yeah. Mathematically, yes. It's practically impossible with standard initialization methods. You are almost surely starting with an injective model.
Wow. Okay, so injectivity is basically guaranteed at the start. It's already a big deal. But here's the clincher, the part that I think really makes this paper stand out. What about training?
Right. That's the critical question. Does gradient descent, which nudges those weights step by step, risk pushing the model onto that dangerous measure 0 collision sheet?
Because if training could break injectivity, the initial guarantee wouldn't mean much in practice.
Exactly. And this is where they do some really elegant mathematical work. They prove that training, whether it's full batch gradient descent or even mini batch SGD, preserves this injectivity. It cannot push you into that collision set.
What's the mechanism? The GD update changes theta. How do they show it doesn't flatten things out?
Well, because the loss function itself and the network are built from these real analytic components, the GD updates, the function that maps the old parameters to the new ones, is also real analytic.
So the update process is smooth too.
Very smooth. The core argument involves looking at the Jacobian of this update map, basically how it stretches or shrinks space locally. They show its determinant isn't always 0.
Meaning it's generally invertible. It doesn't usually collapse volume.
Precisely. It's locally invertible almost everywhere.
Yeah.
Think of it like kneading dough. You can stretch it, fold it, reshape it.
But you can't magically flatten the whole 3D blob into a 2D pancake.
That's a great analogy. The volume might get distorted, but it doesn't disappear. This property, called preservation of absolute continuity, means that if your parameters start spread out in a volume, they stay spread out in a volume after any number of GD steps.
They can't suddenly all collapse onto that measure zero collision surface.
Correct. So the conclusion is really powerful. The final trained parameters, the TAI-T, are still almost surely outside the collision set. Injectivity holds throughout training.
Which means those hidden states aren't just temporary calculations. They remain guaranteed lossless encodings of the input, no matter how much you train the model.
And that theoretical guarantee is what enables the next step, actually getting the input back. Which brings us to SIPIT.
SIPIT. Sequential inverse prompt via iterative updates. Okay, so this is the algorithm that makes the theory real, the tool to recover the prompt from a hidden state, say, HL of S. How does it work? What's the trick?
The trick is causality. It heavily relies on the structure of decoder-only models. Remember, the hidden state at position T, HT, only depends on the tokens before it, S1 to ST1, and the current token, speed.
Right, the standard transformer attention mass.
Exactly. So SIPIT works sequentially. Imagine you've already figured out the first, say, 5 tokens correctly. Let's call that prefix pi.
Okay, pi is SHAT1. SHAT1.
SHAT1?
Yeah.
Now, at step T, you need to find SHAT. SIPIT uses what they call the one-step map. Takes a candidate token, V, from the entire vocabulary.
Like trying out apple, then banana, then cat.
Yeah, for every single word V in the vocabulary, it computes the hidden state that would result at position T if that token followed the prefix pi. Let's call this map F. So F takes V and gives you HT pi concatenated with V.
And because the whole model is injective, this one-step map F must also be injective, right? Each different candidate token V must produce a different hidden state HT.
Yes, almost surely. But it's even stronger than just being unique. They prove there's a positive separation margin, delta, meaning the hidden states produced by 2 different candidate tokens, V and V prime, aren't just different, they're guaranteed to be at least delta distance apart in the hidden state space.
Ah, so there's breathing room between them. That sounds important for robustness.
It's absolutely key. It means even if the hidden state you observed, hat, is slightly noisy or perturbed, you can still reliably find the single correct token.
How does it find it? Does it just compute F for every token in the vocabulary and see which one is closest?
It uses a local verifier. For each candidate token V, it defines a small acceptance region, like a ball, around the predicted state, FD. The radius of this ball, epsilon, has to be smaller than half that separation margin, delta 2.
Okay, so you check. Does my observed state hat fall inside the ball around FV?
Exactly. And because of the separation margin, only the true token's ball can contain hat. It guarantees uniqueness. To avoid checking the whole vocabulary, they use a clever gradient-guided policy to search efficiently.
And this leads to the efficiency guarantee, that linear time complexity, T times V.
That's the worst-case upper bound, yes. It
Yep.
means the total number of these verifier checks across the whole sequence of length T is at most T times the vocabulary size. Linear in sequence length, which is really practical.
It basically confirms that getting the prompt back isn't some theoretical curiosity, it's computationally feasible.
Definitely. It's not like brute forcing combinations, which would be exponential. This is efficient.
Okay, theory sounds solid, algorithm sounds smart, but did they actually test this? Did they try to find collisions?
Oh, did they ever? The scale of the empirical validation here is just wild. You have to appreciate this. They ran over 5 billion pairwise comparisons.
5 billion. Trying to find just one case where 2 different prompts gave the same hidden state?
Yep. Across a whole range of modern models, too. Llama 3.18b, Mistral 7b, 5.4 Mini, Tiny Stories, GPT-2 variants, Gemma models up to 12 billion parameters. They really went for it.
Did they find any?
0. Not a single collision observed. In all those billions of tests, across all models, all layers they checked, distinct prompts always produced distinct last token states.
Wow. And were the states just barely distinct or clearly separated?
Clearly separated. The minimum distances they measured were consistently orders of magnitude larger than their defined collision threshold, which was tiny, like 10 to the minus 6.
So robustly non-colliding.
Absolutely. And interestingly, they often found the separation distance actually increased with model depth and scale.
Wait, really? Deeper layers made the inputs more distinct, not less?
Seems so, based on their plots, which
Yeah.
kind of flips the old intuition about deeper layers meaning more abstraction and compression, doesn't it? Here, depth seems to sharpen the unique encoding.
That is counterintuitive.
Rough.
And did SIPIT itself work in practice? Did it achieve that 100% recovery?
It did. On their test sets, which included meaningful sentences and random token sequences, SIPIT got 100% exact token-level recovery.
And how did it compare to other ways you might try to invert the states?
That's where it really shines. They compared it to a couple of things. A leading gradient-based inversion method called heart prompts. It got 0.00% accuracy, couldn't recover the true input.
Total failure.
Total failure. Then they tried pure brute force search. Now, that can eventually find the right sequence, so it gets 100% accuracy.
But the runtime must be insane.
Astronomical. For one test set, brute force took almost 4,000 seconds. SIPIT, doing the exact same recovery task, took an average of 28 seconds.
Okay, that's night and day. So SIPIT is exact, efficient, and training-free.
That's the takeaway. It makes inversion practical.
Which leads us straight into the broader implications. This feels like it changes things for people actually building and deploying these systems. Let's start with interpretability.
Yeah, this sets a new baseline, I think. If this paper is right, and the hidden states are injective, it means the full input information is there. It's encoded faithfully.
So if your interpretability technique, your probe, or your feature analysis, fails to find evidence of some input detail,
You can't just blame the model for having lost or abstracted away that information anymore. The information is guaranteed to be present. The failure must lie with the interpretability method itself. Maybe it wasn't complex enough or looking in the right way.
it shifts the burden of proof. The state is the input. The challenge is reading it.
Exactly. And that ties into the privacy angle, which is maybe the most jarring implication. The paper puts it bluntly. Hidden states are not extractions, but the prompt in disguise.
That's a strong statement.
Yeah.
How does it clash with, say, current thinking and regulation?
Well, they give an example. Some data protection authorities have argued that model weights might not count as personal data because you can't easily reconstruct the specific training examples from them.
Okay, that argument is about weights and training data.
Right. But this paper focuses on inference time and hidden states. And it proves that from the hidden states generated by a user's prompt, you can trivially, or at least efficiently, with SIP, reconstruct the original prompt.
So if a service provider, say a cloud API, logs or temporarily stores the hidden activations from user prompts,
They're essentially storing efficiently invertible copies of the user's original text input. There's no magical privacy shield just because it went through the transformer layers.
that really ups the stakes for things like prompt deletion requests under GDPR or other privacy laws. If the state is the prompt, you need to handle it like the prompt.
Absolutely. It forces a reconsideration of what data needs protection and how. Of course, the paper notes future work needed extending this to multimodal models, seeing how robust it is to things like quantization.
Which is common in production models, yeah.
But the core mathematical finding for standard transformers is profound. We now know with near certainty that every unique input sequence maps to a unique hidden state.
The mapping is lossless.
Which implies something interesting about the latent space itself, the vast complexity we see there. Maybe it's not some deeply learned, compressed semantic structure in the way we often imagine.
What do you mean?
Maybe it's just a direct injective reflection of the sheer combinatorial complexity of the input sequence space. The model isn't necessarily understanding in a compressive way, it's just learning a unique embedding for every possible input.
And the meaning comes from how those unique embeddings are used to predict the next token.
Perhaps. It's a different way to think about it.
Right.
Which brings us to a final thought for you, the listener, to maybe mull over.
If we accept this paper's finding that every distinct input prompt gets its own unique address, its own distinct point in the hidden state space, guaranteed, what does that really tell us about how LLMs represent semantics?
Is the semantic structure we try to find in the latent space primarily just the model learning to group these perfectly distinct input points based on what they predict next, rather than learning some hierarchical compressed representation of the input's meaning itself?
If the encoding is lossless, maybe the magic isn't in the encoding, but purely in the prediction head, learning to navigate that incredibly detailed injective map of the input space.
Something to consider. Is it complexity reflected or complexity created?
A fascinating question to leave things on. That's all the time we have for this deep dive. We'll see you next time.